Review, a function is even if one, all exponents are even, it can have a constant term. So if, whoa, that's there. In other words, if all of the exponents are even, and you can have a constant term or not, that's an example of an even function. This function is symmetric about the y-axis. It's a mirror image of itself. An odd function only has all exponents are odd. No constant term. That's where it's symmetric about the origin. It can go from first to third quadrant, or it can go from second to fourth quadrant. As long as it goes through the origin. And we're going to look at those in this section. What does transformation mean? There's a movie that came out not too long back called Transformers. Why were they called Transformers? What did they do to make them Transformers? Yes. Transform means to change. That's it. It's a very ambiguous term. What does it mean to change? How can it change? So in mathematics, we have 4 different ways a function can change. We have 4 ways they can change. We can have a horizontal shift. That means the graph moves left and right. We can have a vertical shift. That means it moves up and down. The same picture, it just moves left, right, or up and down. That's so that the picture doesn't change. Next, we can have a horizontal stretch or shrink. That means the graph itself can become wider or it can become narrower. And the last one, we have the vertical stretch or the vertical shrink. Meaning it can change go up and down, or it could be squished together. Those are the four possible changes that can occur in a function. And they can happen all at the same time in some form or another. So how do we know? We're used to seeing equations that look like this. Right? That's what kind of equation is that? What kind of equation is that? To help you determine this, always look at the first term. This is called the leading term. The leading term tells us pretty much everything we need to know about the graph itself. It tells us what kind it is, how many vertices we're going to have, how many times it can cross the x-axis, everything, which direction it goes. What does the constant do for us? The constant, the number at the very end, doesn't have an x. It doesn't have an x. This is the y-intercept. That's all it tells us is where the y-intercept is. If there's no constant, if there's no number at the end of the equation, it goes through the origin. That means your y-intercept is 0. So let's look at the leading term. Well, instead of squared, let's look at the leading term. In general, it'll look this way. A is called the leading coefficient. It tells us the direction. It tells us the size. By size, I mean whether it's going to be big or skinny. The degree is the exponent. The degree tells us number of solutions possible. It tells us the shape of the graph. It tells us the maximum number of vertices. What's a vertex? What's a vertice? We talked about it many times over the last 6 weeks. What's a vertex? A vertice. Very good. It's the max or min, the high or low point of a graph. So the maximum number of vertices is always going to be n minus 1. Remember, the degree is n. That's your exponent. In this column, first column over here, these are my a values. We have two possibilities. A can be positive or A can be negative. Remember, what does A represent? The leading coefficient. It's a number in front of your x value. So it's either going to be a positive or negative. What does n tell us? What does that represent? The degree. That tells us the shape of it. So n can be even or n could be odd. If n is even, what does that tell us? What does that mean for us? Well, a couple of things. If it's even, we know that both ends go in the same direction. If n is even, we know both ends go in the same direction. If n is odd, both ends go in opposite directions. Again, knowing this much is going to show you, you can have a picture of what the graph's going to look like before you ever start doing anything. So if A is positive and n is even, the graph will look like this at the end. This is what's called end behavior. This is what the end of the graphs will look like. If A is the leading coefficient is positive and n is even, we know both ends go the same direction. If A is negative and n is even, then we know that both ends point down. Now, why don't I connect everything here? Because it all depends. Remember, if A was 4, then we'd have 3 bumps. If A is not 8, then we'd have 7 bumps. It's always n minus 1 bumps. Now, if A was positive and n is odd, they point in different directions. The graph looks like this. If A is negative and n is odd, the graph will look like this. Because remember, what we're looking for here is this. We always read left to right. If A is positive, the right side has to be going up. It's positive. It's going up to the right. If A is negative, on the right-hand side, it's going down. If it's even, they're even, they go the same direction. If they're odd, they go opposite direction. So just by giving you any equation now, knowing this, you can have an idea what the graph's going to look like. Before you go any further, and before you do anything, you know what the graph looks like. All right, so that's going to be one thing we're going to need to know. Now let's look at transformations, how this all relates. This is a function. Yeah, we're used to seeing functions like this. Yeah, pretty boring. But this is really what's happening. A, B, C, and D all tell us something different about the graph, what's going to happen to it. Remember, we have 4 things that can happen. These 4 things are dependent on these A, B, C, and D. So let's begin. Okay, note. Here's a note. Any changes inside the function are opposite. And they'll make more sense in a little bit. Any changes outside the function are what they are. This will become more apparent as I show you the examples. But you have to remember this. Any changes that go inside the function are opposites. So let's look at our first one. Horizontal shifts. A horizontal shift is dictated by the C value. This value right here. Notice, C is inside the function. How do we know it's inside the function? It's inside the parentheses. So let's look what this means. Let's say we had f of x equals x squared. That's our function. What does that look like? What's the graph of that one? So what does that mean?
So it's going from infinity to the negative side down to the zero, infinity to the positive.
Right, so it's decreasing to 0 and it's increasing to positive infinity. That's what that graph looks like. Very good. Let me put this down here. Okay. Is there a change inside the function? How do we know it's inside the function? What's that? It's inside the parentheses because the function is the square. Is the square, not the x. The x is just a variable. It's the function is a square. That's what makes it a quadratic equation. Since it's inside, we know it's a horizontal shift. But now, how many spaces in which direction does it move? That's what we have to ask ourselves. When x is 0, we have this point here. So that's, if we set this bottom part equals 0 here, under the square. So what about this part here? We take what's inside there, set it equal to 0. What is my new x value? Solve for x. What do you get?
-3.
Yeah, you subtract 3 from both sides. So x equals -3. This is my new beginning point. It's my new origin. Here, I took the origin from 0, 0. I now moved it 3 spaces to the left. The graph will look the same. It's just, it's shifted 3 to the left. How do I know it's 3 to the left? I give you this. It's opposite. If it happens inside, it's opposite. If this is a +3, then my new origin is at -3. How about this one? What's that graph going to look like? Again, yes, you better memorize your library of functions if you want to make life easier for you. I told you that 5 weeks ago. You had plenty of time to memorize them. So the way you do this, the first thing you do is what's the original function? Looking at this, what's the original function? The square root of x, yeah. You have to know where you're starting off from. What does that graph look like? What's the square root of x look like? Okay, let me ask, if you don't remember, 3 questions you ask yourself. Can x be positive? Can you take a square root of a positive number? Yeah, square root of 4 is what? 2. Can it be 0? Square root of 0 is 0. Can it be negative? No. So we know that it can't be negative. It can be 0 and it can be positive. So plug in some points. When x is 1, y is 1. When x is 4, y is 2. So we know the graph now will look like this. Okay, so first thing to do is find out what is my original library of function. Now, since the only thing happens is inside here, which direction and how many spaces does it go? The number of spaces should be easy. What's the only number we have there? 2. So we know it has to move 2 spaces. Which direction? Y to the right. It's opposite, yeah. So what's inside in here is -2. So my graph has to move 2 spaces to the right. So there's my new origin. So the graph looks the same. It looks like this. All I did was physically move the graph over 2 spaces to the right. What's that graph going to look like? No. I can see why you think it's quadratic because you see a power 2, but x is in the bottom. Remember, whenever you have fractions, what can you not have at the bottom? You cannot have a 0. You cannot have a 0 on the bottom. So what would make 0 on the bottom if x is what? 3. What kind? Positive or negative 3?
Positive.
So we know we have a line that we can't cross because at 3, this is undefined. Originally, the graph would look like this. X cannot be what number? 0. So it can't be here. All we did here was move it to the right 3 spaces. So what's the graph? Can this number ever be negative? Why not? Get used to it. I'm always going to ask you why. Look at, if you put positive 2 in there, what do you get? Positive 2 squared is what? So you get 1/4. Is that positive or negative? Positive. If I put negative 2 in there, negative 2 squared is positive 4. It's still positive. So this graph looks like this. Had you memorized your library of functions? So since we move it 3 spaces to the right, our graph now looks like this. There's our picture. We'll get to that. Very good question. Very good question. Yes, you're thinking ahead there, which is fabulous. And it's, if you think about it now, would that be A, B, C, or D in our function? A, B, or D. If that equation was negative on top, what value would change there? It'd be A, because it changes the sign of the function. Instead of positive, now negative. So we'll get to that point later. All right, so yes, as you can see, you have to know where to begin your graphs to do your horizontal shift. Horizontal shifts happen inside the function, and it's always opposite direction. Let's do a change here. It's still inside the function. Let's talk about reflections. Reflections occur when the sign of X changes. Reflections are mirrors. Let's look at that. So first off, what's the original function from the library of function sheet? Very good. Square root of X. What does that graph look like? Yeah, that's because I just gave you that one, right? It looks like this. Very good. Because remember, the reason being because you cannot have a negative inside a radical. The smallest it can be is 0. But what does our function do? Our function now changes the direction of our graph. How do we get rid of this negative? Well, in order to get rid of this negative, X has to be negative. A negative times a negative is a what? It's positive. So with this, all of my X's have to be negative. So they flip. So this is a flip across the y-axis. Graph this one. So again, always start off with the original function. What's the original function? Square root of X. The square root of X looks like this. Now from there, we build it out. What's the first thing that happens inside there? Well, X changes signs. We're building out this equation. We start off with X. There's a negative in front of it. So what happens to the graph now? It flips across the y-axis. Now we do the rest of the equation. So what happens to the graph there? Which direction does it go?
Three times to the left,
Why do you say to the left?
because the 3 is positive.
I see what you're thinking. But remember, here's the only drawback about that. If we move it 3 to the left, what's going to happen to the numbers? Do we need negative numbers? Yes, we do, because we have to cancel this negative here. So yeah, so yes, you're right there. But here's another way of doing it. You can never go wrong. Whenever you set like this, set it equal to 0. Because remember, you have to start off at the origin, X equals 0. That's where your graph begins. With this equation, if I set it equal to 0, I get x equals 3. So there's my new origin. There's my new origin. So now the graph goes like this. You're right. Yours would have worked, but so would have other numbers. So your logic was correct if it was the other way around, if it was x minus 3, x plus 3. But because we do this, everything changes. So the safest thing to do is whatever's inside here, set it equal to 0. And then this will tell you where your graph starts. That tells you your horizontal shift. Okay, here's another example. Draw this graph. Okay, so the first thing we have to do, what's the original function? Don't know. Very good. Yes, absolute value of x. That's the first one. So what's the graph look like? Looks like a V. Very good. That's the origin. So now what we do is we reflect it. When we reflect it, we flip across the y-axis. So when we flip across the y-axis, what's it going to look like? Itself. Because we flip across the y-axis, nothing changes. There are some functions that reflection doesn't change. The even powers, the even functions, because they're symmetric with the y-axis already. So reflection about the y-axis if the sign of x changes inside the function. In other words, all you do is just flip it across the y-axis. Make sense? If it only changes the sign of x, it only flips across the y-axis. What happens if the sign changes outside the function? Reflections deal with signs changing. That's what reflections deal with. So let's look at here. What's the original function? Absolute value of x. That's that graph. Is there anything happening inside there? Are there any changes inside the function? No. Only change happens outside the function. What that tells us is now all of my y values now become negative. Reflections about the x-axis if the sign change occurs outside the function. So here we flip across the x-axis, and that's our reflection whenever sign changes outside. Let's look at this one. First step, what's the original function? What's that? Yeah, because we see a cubed. So the original function is x cubed. What does that graph look like? Yes, snake going up as opposed to snake going to the right. So that's our first thing we look at. What's the original function? Now, the second thing we look at, are there any sign changes inside the parenthesis? Is x changing sign inside the parenthesis? No, it's still positive. So now we look at a horizontal shift. If it happens inside, it's a horizontal shift. So which direction, how many spaces? Right, y to the left.
Because inside is the opposite.
Right, because it's a +3, so I go -3. So there's my new origin. My origin shifts from here, it shifts 3 spaces to there. So the graph so far looks like this. Are we done yet? No, there's a negative out in front. So the third change happens outside there. If it happens outside the function, what happens to the graph? It goes where? It flips across the x-axis, yes. Like a bicycle pedal. You push this one down, so it now looks like this. Instead of being an increasing function where it goes up to the left, it now goes down to the left. It's a decreasing function. And there's your new graph. Just by looking at them, this is what we're telling us. So far, so good? Okay, so we've talked about horizontal shifts. We've talked about reflections. Let's talk about vertical shifts. A vertical shift happens outside and away from the function. Happens outside and away. So looking at our, so looking at our function, which letter is it? A, B, C, or D? Well, we talked about C already, so that can't be it. So what would be vertical shifts? Outside and away from the function. What's the only one that's outside and away from the function?
Plus B.
D. Anything plus and minus to the equation is a vertical shift. So that's our D value. Since it happens outside the function, it is what it is. So looking at this one, x squared plus 2. First thing, what's the original function look like? X squared. And so that is a parabola. Work our way out. Is there anything inside the function? No. So there's no horizontal shift or any horizontal reflection. Is there a negative in front of the function? So there's no vertical flip. All there is a 2. What that tells us is, since it's positive, we go up 2 spaces. So this, my origin goes from here, it goes up to 2 spaces there, and my graph now looks like this. It just physically lifts it up 2 spaces. Hence, vertical shift. Let's look at this one. So what's my original function? One over x. What does 1 over x look like? What's the graph look like? Very good. Yeah, the boomerang is opposites, right? If x is positive, the answer is positive. If x is negative, the answer is negative. Is there a horizontal shift? When we ask, is there a horizontal shift? Is there a parenthesis around the x? Does it have any numbers around the x? No, so there's no horizontal shift. Is there a reflection? In other words, when we said there are 2 different reflections, does x change sign? Is it a negative x? No. Is there a negative in front of the function? That answers your question earlier. What happens if it's a negative? It flips across the x-axis. So all we have left is this. So what does that tell me to do? Just go down 3 stages. Here's -3. So there's my new origin. The graph looks the same. It's just shifted down 3 spaces. Let's look some more. There. First thing, what's the original graph of this function? Absolute value of x. It's a v. Very good. Check. Oh, I hate that camera. 2. Now we look inside the function. What does that tell me to do? So I'm looking here. Is this a horizontal or vertical shift? Why? Very good, because it's inside. Which direction? How many spaces?
2 spaces to the right.
Right, because if we took inside there, set it equal to 0, we get x equals 2. That's my new origin. Is that 2? The graph still looks the same. Remember, we're building ourselves out of there. So our third step, we got the x minus 2. Now we have a negative in front of the x minus 2. What does that tell me to do? Upside down. So we do, right. We flip across the x-axis. Excellent. Very good. Very good. This negative tells me flip across the x-axis. It happens outside the function. So the next one is the -3. What does this -3 tell us to do?
Shift it down 3 times.
Right. So physically move it down 3 spaces. So there's our new origin is right there. So our graph looks like that. What do y'all think so far? Pretty straightforward? All right. So far we've discussed what letters? C and D. Because we have A, F of B, X plus C plus D. We've only talked about C and D. We've kind of talked about B and A, only the sign changes. So C tells us the horizontal shift. D tells us the vertical shift. Now, the question is, do we want to do horizontal or vertical transformations now? Let's start with his horizontal. Let's now look at B. Remember, if it happens inside, what happens? What do we do if it happens inside? It's always, is it same or opposite? It's opposite. So if we had if we had 3x squared, I had to give you some of the stuff. What would my point be now? What would my graph? So the original graph is x squared. It's a parabola. So what do you think happens to my graph if I multiply it the x side?
Does it expand or?
What's gonna happen is whatever's gonna happen is gonna be horizontal because it happens inside there. Since it's a horizontal, since it happens inside the function, it's horizontal, which means it's either gonna become skinnier or it's gonna become fatter. What do you think? Ooh, we have a smackdown now. Well, think about this. If we had at 2, x squared at 2 is what? If x is 2, what's x squared? If we take x is 2, square it, what do we get? 4. Now, here, 3 times 2 is, remember, we're still at the number 2. But 3 times 2 is 6. 6 squared is 36. So it becomes a lot skinnier. Actually becomes 3 times skinnier. So because it's an integer, because it's greater than 1, it gets skinnier. If we had let's say 1/5. If we had 1/5, what would happen there? The graph would be much wider. Because when x is 1, y is 1/5. It's less than 1. It's 1/5 squared. When x is 2, 2/5 squared is 4/25. So that's pretty small also. So we're looking at it grows very, we haven't gotten to 1 yet. If you don't see it, plot some points. And you'll see that since if it's an integer, the numbers grow really fast. If it's a fraction, it grows really slow up. So let me put this in work. Horizontal shrinking and stretching. Now, I'll do the next. So this is whenever we have a coefficient in front of our x. F of x shrinks horizontally for any absolute value of b greater than 1. What does it mean shrink? Horizontally shrink means it gets skinnier. It stretches horizontally for any b absolute value of b value. If it's between 0 and 1, what does that mean? This is decimal, it's a fraction. So if it's bigger than 1, it shrinks. If it's less than 1, it gets wider. And we're gonna do a graph completely looking at these in a second. Remember, what these are talking about is if your x has a coefficient. If it's an integer bigger than 1, that means the graph's gonna get skinnier. If it's a fraction in front of your x, it'll get wider. So from what we do here, these are how you transform the points. This is your original function. Whatever b is, the new value of x is going to be x divided by b. Why is it divided by b? Because remember, it's inside the operation, it's always the opposite. If bx equals 1, then x equals 1 over b. It's the reciprocal of it. It's always, if it happens inside, it's always opposite. And then we're going to look at vertical shrinking and stretching. Remember, if it's vertical, does it happen inside or outside? Outside. So what this one deals with, this is the a value. It stretches vertically for any absolute value of a bigger than 1. In other words, if your coefficient is an integer or a number bigger than 1, that means your graph will be pulled up and down. It will shrink vertically for any absolute value of a between 0 and 1. Which makes sense. But think about it. If your original function was f of x, we had x, y. All it does is change your y values. The number in front changes your y values. How do we know that? What does this mean? What does f of x stand for? It stands for y. So if you have a coefficient, this is the same thing as a times y. All it changes is the y value. Where is that? Okay, in your packet, we have this example sheet. It's the last couple of pages. So here's our function, whatever the function is. Remember, all the horizontal and vertical shifts do, the transformations, is they change the x and y values. So A, the first one we have here, we want 2f of x. So what does that tell us to do? If it's 2f of x, what does it do to our graph? What values does it change in our graph? The y values. So what does it do to the y values? It multiplies them by 2. So with the first one, so all this tells me is all of my y values I multiply by 2. So in the first one, we have negative 5, 0. So that stays at negative 5, 0. 0 times 2 is 0. How about negative 2, 2? What happens to that one? What does this tell me to do? Yeah, so it's negative 2. 2 times 2 is 4. So now I go from negative 2 to 4. Zero, zero, it stays there. What happens at 2, negative 4, if this is my function? What's the new point here? 2, negative 8. It used to be 2, negative 4, but now I multiply negative 4 by 2 is 2, negative 8. And then it stays at 4, 0. So what happened to the graph there? Did it shrink or stretch? Which direction? Remember, the original one looks like this. The original one looks like this. So that dotted line is the original one. So what happened to the graph? Since it happened outside, is that horizontal or vertical? Vertical. Since it's an integer, it stretched it vertical. It took the graph and pulled it up and down. It stretched it vertically. It's a vertical stretch. B is saying 1/2 f of x. So let me put the original functions on here also. So we have negative 5, 0. We have 2, 2, 0, 0. 2, negative 4. So there's the original function. This is a straight line. This is a straight line. This is a curve. So what does this one tell me to do? Take all the y values divided by 2. That's what it tells us. So 5, 0 stays the same. Negative 2, 2 becomes what? Negative 2, 1. Very good. Zero, 0 stays there. Negative 2, negative 4 becomes 2, negative 2. All you're doing is changing the y values. So because my eighth term was this is a vertical shrink. So again, if it happens outside, it's vertical. If it's an integer, multiply 2 to each y term. That's all you do. This one, I divide all the y values by 2. All right, let me draw this graph in the next picture. So that's negative 5, 0. Yeah. So negative 5, 0, negative 2, 2, 0, 0, 2, negative 4. So that's the original function. What this one's asking for is f of 2x. F of 2x. So what do you think is going to happen here? Keeping in mind what we talked about already, is the graph, is the new graph going to be smaller or larger than this one? Smaller. Smaller by how much? Half. Because what this thing tells me to do, since it happens inside, and remember, whatever you do inside is opposite. Since this is 2 times x, what do we do to my x values? Divide them by 2. So my x value here is negative 5. Negative 5 divided by 2 is 2.5. So my first x value is right there. This x value is 2. Divided by 2, I get 1. This one's 2. Divided by 2, I get 1. So my new point is right here. So it's a horizontal shrink. Says divide each x by 2. It's a horizontal shrink. Because remember, if it happens inside, it's opposite of what's supposed to happen. So you notice the y values never changed. The high and low would never change. All we did was compress it like an accordion. The next one is f of 1/2 x. So what do you think we do here to my x values? What's that? Multiply by 2. Do we change the y values? No, we don't change the y values because the only change happens inside the function, and that's what x is. So it starts off at 5, 0, negative 2, 2, 2, 4. So this is my original graph. So the first one, negative 5 becomes what? It becomes negative 10. Very good. Here you multiply each x by 2. So the first one becomes 10, 0. Next one is at negative 2, 2. This becomes negative 4, 2. The 0, 0 stays there. 2 becomes 4, so we have a point there. And 4 becomes 8. 8. So this is a horizontal stretch. Because if it happens inside, it's opposite of what it tells me to do. And the last one is negative 1/2 x. So what do you think happens here?
Multiplied by -2.
Okay. Yes. So the first point was we had negative 5, 0, negative 2, 2, 0, 0. Right. So our x values, negative 5 times negative 2 is positive 10. The next point, negative 2. Negative 2 times negative 2 is positive 4. So it's 4, 2. 0, 0. So this one looks like this. At 2, negative 4, take 2, multiply by negative 2, we get negative 4. Negative 4, negative 4. And that 4 times negative 2 is negative 8. I should have used. So this is my new graph. All you do here is multiply each x by negative 2. It's not really, well, where it's fortunate, it's 1/2. What if I gave you this? What would you multiply each x with?
5.
Multiply each x by 5/3. The reason this one is 2 is because we take 1/2 and flip it, it's 2. So it's whatever you have here, flip it, and that's what you multiply each x value with. So that's It's not always the bottom number. It's the refraction, the reciprocal of that fraction. So here we multiply each 1%. It'd be negative 5/3. Right. The sign doesn't change. All the sign does is now put it up, whether it's left or right up or down. So that's the transformation section. It's not intuitive. It's not just straightforward. Well, the first parts were the horizontal shift, the vertical shift, the reflections. Those are pretty intuitive. These other transformations are pretty complex. These other transformations, these are more difficult because now we have to look at, is it a horizontal stretch or shrink, or is it vertical? And it's always opposites. Okay, so, and this one up here was this new graph here. So if you notice both of these graphs, what's different about them? Remember, what happened when you have a negative in front of your x? What did we do earlier?
Over the y-axis.
Right, it's a reflection across the y-axis. So we flip it across the y-axis. And that's what we did here. We took this graph, flipped it across the y-axis, and there we have that. But yeah, there are a lot of moving parts, which you have to be very careful, and very careful and cognizant of what's going on here when you do each of these changes. Any questions? Comments, threats, bribes? Okay, well, that's the end of this section and end of this chapter.